What if the universe is a beautiful musical piece akin to the likes of Mozart, and we're just beginning to decipher the score? What if a single, elegant equation could explain everything from the whisper of a falling leaf to the roar of a supernova? Welcome back to Stellar Stories, where we delve into the deepest mysteries of existence. Today, we're on a quest for the holy grail of physics, the theory of everything. Prepare to journey through the minds of geniuses, explore cutting-edge science, and confront the mind-bending possibilities of reality. Today we'll be looking at mankind's relentless pursuit of a theory of everything. What if everything, the very fabric of reality, from the smallest quark to the largest galaxy, could be explained by a single, elegant equation, a master key that unlocks the secrets of the universe? For millennia, humanity has chased this elusive dream. From the ancient philosophers who sought the fundamental building blocks of existence, to the revolutionary minds who shattered our understanding of space and time, to the modern physicists grappling with the mysteries of quantum mechanics and the cosmos. We'll be looking at the ancients and their perspectives on reality. We'll be exploring potential candidates for the theory of everything, from string theory to causal set theory. So if that's your thing, you may want to stay tuned. Let's face it, we're all obsessed with the universe, always have been. From the dawn of time, humans have stared up at the cosmos, wondering what it all means. Stars, planets, the whole shebang. We wanted answers, and before we had fancy labs or telescopes, we had something even more powerful. Pure, unadulterated curiosity. That's where the pre-Socratic philosophers come in. These guys were the original cosmic thinkers, the ones who dared to ask the big questions. They were the pioneers, laying the groundwork for everything we know today. So, where does it all begin? Imagine going back to the very dawn of philosophical thought. One of the first to take a stab at the universe's biggest question was Thales of Miletus. His answer? Water. Yep, good old H2O. He thought everything, from a tiny raindrop to the colossal mountains, was just water in disguise. It might sound crazy now, but he was reaching for a fundamental truth. Then came Anaximander, who took it even further, suggesting the universe sprang from something even more abstract. An infinite, boundless apeiron. That was the Greek word for infinity, so it's not too far of a stretch to link it to modern cosmology. After all, the Big Bang Theory is said to have exploded from a singularity, which can be thought of as a state of infinite density. These guys were sort of just guessing, but they were laying down the first bold strokes in our cosmic quest. Plato had a theory, and it's way ahead of its time. He introduced the demiurge, a mysterious craftsman who didn't create matter, but rather imposed order on a pre-existing chaos. Imagine a swirling, chaotic mess being sculpted into something beautiful and structured. That's Plato's vision. This demiurge used eternal forms, which he believed to be perfect, unchanging archetypes of everything. He shaped the universe, or to use the Greek word, cosmos, into a living being, a harmonious and orderly creation, all driven by a grand design to achieve good effects. Plato's cosmos isn't just a place, it's a carefully constructed reality, imbued with purpose and mathematical beauty. The quest for a theory of everything has been a long and winding road, but it has been a journey marked by human curiosity, ingenuity, and a relentless pursuit of knowledge. As we delve deeper into the mysteries of the universe, we continue to build upon the foundations laid by these early thinkers, seeking to unravel the secrets of the cosmos and our place within it. The Middle Ages saw a shift in focus from the purely philosophical to a more theological perspective. The prevailing worldview was heavily influenced by religious doctrines, with the Earth often viewed as the center of the universe, a concept known as geocentrism. This view was eloquently articulated by Ptolemy in his work Almagest, which became the standard astronomical text for centuries. Any deviation to this religious dogma could lead to imprisonment, exile, or even execution, as many thousands found out to their detriment. But the seeds of change were already being sown. During the Renaissance, a renewed interest in classical Greek and Roman thought sparked a revival of scientific inquiry. Scholars began to question traditional beliefs and to challenge the established order. Figures like Nicolaus Copernicus, with his heliocentric model of the solar system, and Galileo Galilei, with his observations through the telescope, began to overturn the old geocentric worldview. These pioneering thinkers, along with others like Johannes Kepler and Isaac Newton, laid the foundation for modern science. Their work challenged the established order, sparked intellectual revolutions, and paved the way for our current understanding of the universe. As we move further into the future, we continue to build upon the foundations laid by these early thinkers, seeking to unravel the mysteries of the cosmos and our place within it. The quest for a theory of everything remains an ongoing endeavor, a testament to the enduring human desire to understand the universe and our place within it. If you've got this far, I'd very briefly like to say, if you like what you see, please consider liking, subscribing, or leaving a comment. This is still a tiny channel, and every interaction from you helps immensely, and the benefit of being a tiny channel is that I can respond to you all. With that said, let's continue. The 19th century witnessed a remarkable convergence of scientific discoveries that began to reveal a deeper order beneath the surface of the natural world. One of the most significant breakthroughs was the unification of electricity and magnetism by James Clerk Maxwell. His elegant set of equations, now known as Maxwell's equations, demonstrated that these two seemingly disparate forces were intimately connected, forming a single electromagnetic force. This discovery not only revolutionized our understanding of light and electromagnetic waves, but also laid the groundwork for technologies that would transform modern society, from radio and television to the internet and smartphones. Another major development during this period was the formulation of the laws of thermodynamics. These laws describe the behavior of heat and energy, providing a framework for understanding how energy is transferred, transformed, and conserved within systems. The first law of thermodynamics, the law of conservation of energy, states that energy cannot be created or destroyed, only transformed from one form to another. The second law of thermodynamics introduces the concept of entropy, a measure of the disorder or randomness within a system. This law states that the total entropy of an isolated system always increases over time, meaning that the universe tends towards a state of increasing disorder. The discoveries of electromagnetism and thermodynamics, along with other scientific advancements of the 19th century, provided compelling evidence for the underlying order and interconnectedness of the natural world. These discoveries forced thinkers of the time to reconsider the prevailing mechanistic worldview and paved the way for a deeper understanding of the fundamental forces that govern the universe. As we move into the 20th century, we will witness even more revolutionary breakthroughs in our understanding of the universe, culminating in the development of two groundbreaking theories, relativity and quantum mechanics. These theories, while seemingly contradictory, would offer new insights into the nature of space, time, and the very fabric of reality. Einstein's theory of relativity, published in two parts as the special theory of relativity in 1905, brought chaos to the Newtonian worldview of absolute space and time. Special relativity demonstrated that the laws of physics are the same for all observers in uniform motion, and that the speed of light in a vacuum is constant regardless of the observer's motion. This led to the famous equation E equals mc squared, which revealed the equivalence of mass and energy. General relativity, on the other hand, presented a radically new understanding of gravity. Einstein proposed that gravity is not a force, but a curvature of space-time caused by the presence of mass and energy. This theory not only explained the motion of planets and stars, but also predicted the existence of black holes, gravitational waves, and the expansion of the universe. While relativity revolutionized our understanding of the large-scale structure of the universe, quantum mechanics delved into the realm of the very small. This theory, born from the study of atomic and subatomic phenomena, revealed a world that defies our everyday intuition. Concepts such as wave-particle duality, superposition, and entanglement challenge the classical notions of determinism and causality. Quantum mechanics, with its inherent uncertainty and probabilistic nature, puzzled the physicists of the time with its implications about the nature of reality. Does reality exist independently of observation, or is it shaped by the act of measurement? Can objects exist in multiple states simultaneously until they are measured? These questions continue to baffle scientists and philosophers alike. This quest for unification has driven much of modern physics research, leading to the development of various candidate theories, such as string theory and loop quantum gravity, which we will now explore. String theory emerged as a bold attempt to address this fundamental challenge. At its core, string theory proposes that the fundamental building blocks of the universe are not point-like particles, as in conventional physics, but rather tiny, one-dimensional, vibrating strings. These strings, thought to be incredibly small, on the order of the Planck length, can vibrate in different ways, giving rise to the various particles and forces we observe in nature. The elegance of string theory lies in its potential to unify all the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. By treating these forces as different vibrational modes of the same fundamental object, the string, string theory offers a framework for a unified description of the universe. However, string theory is not without its problems. One of the major hurdles is that it requires a staggering number of extra dimensions beyond the 3 spatial dimensions and one-time dimension that we experience. These extra dimensions are thought to be compactified, meaning they are curled up into tiny, imperceptible spaces. Furthermore, string theory involves complex mathematical concepts and abstract structures. The development of the theory has led to significant advancements in mathematics, but it also presents a steep learning curve for those seeking to understand its intricacies. Despite these seemingly insurmountable hurdles, string theory remains a leading candidate for a theory of everything, offering a tantalizing glimpse into the fundamental nature of reality. However, it's important to acknowledge that string theory has faced increasing criticism in recent years. One major concern is the lack of experimental evidence to support its claims. The energy scales required to directly observe string theory effects are far beyond the reach of current and foreseeable technology. This lack of empirical support has led many physicists to question the viability of string theory as a viable path towards a unified theory. Moreover, the sheer number of possible string theory solutions, often referred to as the landscape of string theory, has raised concerns about the theory's predictive power. With such a vast number of possible universes, it becomes difficult to make specific, testable predictions that can be compared to observations. As a result, many theorists are now exploring alternative approaches, such as loop quantum gravity, which offer different perspectives on the unification of physics. While string theory remains a fascinating and mathematically elegant framework, its future as the leading contender for a theory of everything remains uncertain. String theory represents a bold and ambitious attempt to reconcile the seemingly contradictory pillars of modern physics. While it offers a tantalizing glimpse into the fundamental nature of reality, the lack of experimental evidence and the issues associated with its mathematical complexity have led many physicists to explore alternative avenues in the ongoing quest for a unified understanding of the universe. While string theory attempts to unify physics by proposing that fundamental particles are actually tiny vibrating strings, another promising approach is loop quantum gravity. It takes a different route, seeking to reconcile general relativity and quantum mechanics by quantizing space-time itself. Instead of treating space-time as a smooth, continuous fabric, as in classical physics, it proposes that space-time is fundamentally granular, composed of discrete loops and networks of these loops. These loops, or quantum loops, are the fundamental building blocks of reality, and their interconnectedness forms the fabric of space-time. One of the key features of the theory is that it naturally incorporates the principles of quantum mechanics. The properties of space-time, such as its geometry and topology, become quantized, meaning they can only take on certain discrete values. This quantization of space-time leads to a fundamentally different picture of the universe at the smallest scales. It also offers a potential resolution to the singularities that arise in general relativity, such as those found within black holes. In loop quantum gravity, the concept of a singularity is replaced by a highly curved but finite region of space-time. This avoids the mathematical inconsistencies that arise in classical general relativity when attempting to describe the physics at the center of a black hole. While loop quantum gravity offers a promising framework for a quantum theory of gravity, it also faces challenges. Like string theory, the mathematical complexity of the theory is considerable, making it difficult to make concrete predictions or to test its validity experimentally. Furthermore, it requires a deep understanding of advanced mathematical concepts, making it inaccessible to many physicists. Despite this, it remains an active area of research, with ongoing efforts to develop the theory further and to explore its observational implications. While a definitive theory of everything may still be out of reach, the pursuit of such ambitious theories continues to push the boundaries of our notions of the universe and its fundamental laws. While string theory and loop quantum gravity are prominent contenders in the search for a theory of everything, they are not the only approaches being explored by physicists. A diverse landscape of other theoretical frameworks is being investigated, each offering unique perspectives and insights into the fundamental nature of reality. One such candidate is causal set theory. This approach proposes that space-time itself is not continuous, but rather a discrete network of events. These events are not points in space and time, but rather fundamental building blocks of reality connected by causal relationships. In this framework, the laws of physics emerge from the underlying structure of this causal set. Another intriguing possibility is asymptotic safety. This theory suggests that the fundamental forces of nature, such as gravity and the other fundamental forces, might have a fixed point in their behavior at very high energies. This fixed point would represent a stable and predictable state of the universe, providing a framework for understanding the behavior of these forces under extreme conditions. While these theories are still under development, they offer alternative perspectives on the problem of unifying gravity and quantum mechanics. They demonstrate the ongoing pursuit of a deeper understanding of the universe, a quest that continues to push the boundaries of human knowledge and imagination. One intriguing philosophical concept that has emerged from these considerations is panpsychism. This view suggests that consciousness is not a unique property of complex organisms like humans, but rather a fundamental property of the universe itself. In other words, consciousness is inherent in all matter, from the smallest subatomic particles to the largest celestial bodies. While panpsychism remains a highly speculative idea, it confronts our traditional understanding of consciousness and its place in the universe. It raises the possibility that the universe itself might be imbued with some form of sentience, a concept that is both awe-inspiring and deeply unsettling. Another important concept to consider is the hard problem of consciousness, a term coined by philosopher David Chalmers. This refers to the fundamental mystery of how physical processes in the brain give rise to subjective experience, to the qualia of consciousness, the redness of red, the sweetness of sugar, the feeling of pain. While neuroscience has made significant strides in understanding the neural correlates of consciousness, the question of how these neural processes translate into subjective experience remains unanswered. While mainstream physics grapples with reconciling relativity and quantum mechanics, some theorists venture beyond the conventional, exploring more radical and philosophical frameworks. One such example is Tom Campbell's My Big Toe, which stands for Theory of Everything. Campbell's theory delves into the nature of consciousness, proposing that it is a fundamental aspect of reality, not an emergent property of complex biological systems. He suggests that consciousness is a field similar to the electromagnetic field that permeates the entire universe. This field, he argues, is the basis of all existence, giving rise to both matter and energy. Campbell's theory incorporates elements of quantum mechanics, suggesting that consciousness plays a role in shaping the reality we perceive. He proposes that our observations and choices influence the outcomes of quantum events, suggesting a form of consciousness-based reality. While My Big Toe is a highly speculative theory, it flies in the face of conventional thinking about the nature of reality and the role of consciousness in the universe. It raises profound questions about our place in the cosmos and the relationship between mind and matter. Campbell's theory, while controversial, demonstrates the breadth and depth of the search for a theory of everything. It highlights the fact that this quest extends beyond the realm of traditional physics, encompassing philosophical and metaphysical considerations. The search for a theory of everything is not merely a scientific endeavor, it is a philosophical and existential quest that forces us to confront the deepest questions about our existence and our place in the grand scheme of the universe. One of the most provocative ideas to emerge from this exploration is the simulation hypothesis. This mind-bending concept proposes that our perceived reality might be a computer simulation, a complex program created by a more advanced civilization. This simulated reality could be so intricate that we are completely unaware of its artificial nature, experiencing it as genuine reality. The simulation hypothesis is not the only metaphysical theory that questions our beliefs and ideas of reality. The concept of emergent properties suggests that complex systems can exhibit properties that are not present in their individual components. For example, consciousness, a complex phenomenon, may emerge from the intricate network of neurons in the brain, even though individual neurons themselves do not possess consciousness. Similarly, the laws of physics themselves may be emergent properties of a more fundamental underlying reality. The human quest for meaning has driven us to explore the universe, to understand our place within it, and to seek answers to the fundamental questions of existence. Science, with its relentless pursuit of knowledge and its capacity to unveil the hidden workings of the universe, plays a crucial role in this quest. However, the search for meaning extends beyond the realm of science. Philosophy, religion, and art all offer different perspectives on the human condition, exploring questions of existence, purpose, and the nature of reality. These different ways of knowing, while often distinct, can also be complementary, offering different lenses through which to view the universe and our place within it. As we continue to explore the cosmos and delve deeper into the mysteries of existence, we are reminded of the interconnectedness of all things. The universe, with its vastness and complexity, is a testament to the power of creation, a symphony of forces and energies that has given rise to life, consciousness, and the capacity for wonder. As we gaze upon the stars and contemplate the vastness of the universe, we are left with a perplexing question. What is our responsibility as a species in this vast and intertwined cosmos? Are we stewards of the universe, tasked with protecting and preserving the delicate balance of life? Or are we simply a fleeting moment in the grand cosmic narrative, destined to fade into oblivion? We've journeyed through the triumphs and tribulations of scientific discovery, from the unification of electricity and magnetism to the mind-bending concepts of relativity and quantum mechanics. We've grappled with the gripping questions posed by these theories, exploring the nature of reality, the role of consciousness, and the possibility of a simulated universe. But the search for a theory of everything is far from over. It's an ongoing process, a monument to humanity's insatiable curiosity and our relentless pursuit of knowledge. As we continue to explore the cosmos and delve deeper into the mysteries of the universe, we may one day achieve a unified understanding of the fundamental laws that govern reality. The universe is a symphony of interconnected forces, a masterpiece of creation waiting to be fully understood. And while the answers may still lie beyond our grasp, the journey itself is a testament to the power of human ingenuity and the enduring human spirit. See you next time.